The video in the series ANSYS tutorials. The aim of this video is to get familiar with ANSYS Workbench and how is ANSYS workflow, and we will do it by meshing some simple geometries. My presentation includes meshing capabilities in ANSYS Workbench, processing workflow, mesh method, mesh metric, and meshing some cases, some examples. ANSYS Fluent is the leading computational fluid dynamics software widely used in industry and academia for fluid simulation. It's known for its advanced physics modeling capabilities and best-in-class accuracy. The goal of meshing in ANSYS, particularly for ANSYS Fluent, is to divide the computational domain into smaller subvolumes where the equations of fluid dynamics can be solved to obtain the behavior of a fluid as it flows around an object. Meshing is a crucial step in the simulation process because it converts irregular shapes into a finite number of standard elements that the solver can work with more easily. As explaining the processing workflow, as you can see, first of all, we should create or import our geometry. You can create the geometry in a CAD software or import an existing one into ANSYS Fluent. Ensure the geometry is clean in this section in geometry modification, and watertight to avoid issues during meshing. And in this section you can generate mesh, use the watertight geometry meshing workflow to create a high quality mesh, adjust the mesh to ensure it captures all the necessary details of the geometry, and after you create your geometry and meshing that, you can set up the physical models required for your simulation, such as laminar models, heat transfer, and multi-phase flues. Set boundary conditions in this section, and then initialize the flue field to provide a starting point for the solver. Execute the solver to perform the simulation, mount convergence, and adjust the solver settings if necessary. And finally, make necessary adjustment to the model and rerun simulation to improve accuracy. According to your geometry, you can use two-dimensional meshes or three-dimensional meshes. For 2D meshes, you can use a quadrilateral or triangle elements, triangle cells, as you can see, and in 3D meshes you can use hexahedral, tetrahedral, pyramid, wedge, polyhedral cells, as you can see in this picture. 3D elements should be used when all dimensions of a component are comparable in X, Y, and Z. When quad element is extruded like that, the hex element will be formed, as you can see. And there are different types of methods to mesh your geometry, including tetrahedrons, hex dominant, sweep method, multi-zone, Cartesian method control, layer tetrahedrons method control. For a multi-zone, this mesh method provides automatic decomposition of geometry into mapped regions and free regions. When the multi-zone mesh method is selected, all regions are meshed with a pure hexahedral mesh if possible. It used hexahedral mesh as much as possible. To handle cases in which a pure hex mesh won't be possible, you can adjust your settings so that a sweep mesh will be generated in structured regions and a free mesh will be generated in unstructured regions. The Cartesian method creates unstructured hex mesh of mostly uniform size aligned to the specified coordinate um, system and fits it to the geometry. And the layered tetrahedrons method control the layered tetrahedrons mesh method creates unstructured tetrahedral mesh in layers based on a specified layer height, and as you can see in this picture, and fits it to the geometry. After you meshing your geometry, you should check the quality of your mesh. There are some parameters, some important parameters that you should check for your geometry as element quality, aspect ratio, Jacobian ratio, warping factor, parallel deviation, maximum corner angle, skewness, and orthogonal quality. The element quality option provides a composite quality metric that ranges between 0 and 1. This metric is based on the ratio of the volume um, to the sum of the square of the edge lengths for 2D quadri elements, um, the ratio of area to uh, that, and or the square root of the cube of the sum of the square of the edge lengths for 3D elements. If you use the 3D meshes, so you this the formula can help. A value of 1 indicates a perfect cube or square, while when you reach 0, the element has a 0 or negative volume, and it couldn't be acceptable. For aspect ratio, it can be defined as the maximum element edge length to minimum element edge length. As you can see in this picture, this ratio is equal to 1, but in that it is more than 1, and it would be acceptable when it is below 5. And a Jacobian ratio is a measurement of the shape of a given element compared to that of an ideal element. The ideal shape of an element depends on element type. The ideal Jacobian ratio is equal to 1, and it would be acceptable when it is above 0.6. It could be seen that in this picture for tri-elements it's equal to 1, for a square it's equal to 1, but it is approaching 0 for that, and it couldn't be acceptable, and it should be degenerate. You should degenerate your mesh. Warping is a measure of twisting and distortion, and is best understood by looking at quadrilaterals with varying warping factors. The ideal warping factor is 0 for that, but it in these shapes they are twisting, so it could be equal to 0.2 or 0.4 for that one. And parallel deviation is a measure of how much two parallel sides of a shape like that deviate. The ideal parallel deviation is equal to 0 for square, as you can see, but in these pictures they are deviated, and it could be 70 or odd numbers, as you can see. Maximum angle between adjacent edges of an element for triangle, the best maximum angle is 60 degrees. This angle, I mean. But in this picture it's equal to that number. So maximum corner angle demonstrates the angle between the maximum angle between adjacent edges, as you can see. Another important parameter is skewness. Is one of the primary quality measures for a mesh. Skewness determines how close to ideal a face or cell is. As you can see, this is the ideal one, but it is highly skewed triangle, highly skewed quad, as you can see, and it could be acceptable when it's below 0.75, but when it reaches 1, you should generate your mesh. Orthogonal quality, as you can see in this picture, in this element, I want to define three vectors A, F, and C. I want to explain how we can compute the orthogonal quality or the software computed. As you can see, the vector A is the face normal factor. It's normal to this face, as you can see. And C is the vector from the cell centroid, as you can see, to the centroid of each of the adjacent cells, like that, centroid of this cell. And F for each face, the vector F from the cell centroid to each of the faces. And the angle between A and C and A and F can be calculated, the cosines of the angle between them. And the smallest calculated cosine value is the orthogonality of the cell. It's the definition of orthogonal quality. This value ranges between 0 and 1, where a value of 0 is worst and a value of 1 is best. Finally, I want to give some points about how not to mesh, and after you meshing your geometry, you should check the mesh of your geometry when you have triangles like that, as you can see in this picture, and they are connected back to back. It should be avoided, and in addition, they shouldn't be connected to each other directly like that. These elements, these tri-elements like that, so it's wrong. Or on plane surfaces, triangular element should be avoided. Simple shape like that is a plane surface, and it's a simple geometry. You cannot use tri-elements like that in this picture. And about holes, when you have holes in your geometry, you should model it carefully with a washer, as you can see, like that, with a washer. So the diameter of a washer, like that, that surrounded this hole, should be 1.5 to 2 times more than this diameter. If this diameter is equal to 1 centimeters, this should be 1.5 or 2 centimeters. And the number of elements that surround that, in addition, you should use a minimum layers of 2 layers around that, 1 and 2. A minimum of that is 2. It could be more than that. And the number of elements that surrounded these holes, it should be an even number. You cannot use that one. It's not true because it's 7, but you should use these numbers, even numbers, for that picture. More importantly, no tri-elements should be on the feature and the fillet. The stiffness of tri-elements can lead to inaccuracies in simulation results, especially in areas of high stress concentration, such as near hole or fillet, because they cannot accurately model the complex formation. As you can see, you cannot use tri-elements like that around this hole. And to to explain it in more detail, you can see in this picture. When you use three tri edges like that, tri element like that, when a force is applied in to the node M3, there are only three nodes available to define that plane. To define that plane, xy plane, you need 3 points. So when F applied to N3, N3 cannot bending or moving to the YZ plane. So it is going to transfer the load to N1 and N2, as you can see. But in this picture, for quad elements, when first F is applied to N3, you can see the node N3 can move in YZ plane as node N1, N2, and N4 has already defined the XY plane. To define XY plane, 3 points is essential and is enough. So N1, N2, and N4 has already defined XY planes. So N3 can bending and moving in along XY. So when the first F is applied at the node N3, this node can move in the YZ plane as node N1, N2, and N4 has already defined the XY plane. As a result, we have N1, N2, and N4 in XY along with N2, N3, and N4 in the other plane. N2, N3 in Z, N4 in XY. Thus, having the nodes in two planes causes the bending in quad elements. In the next presentation, we mesh some geometry and explain the methods, the different methods that we presented in at the previous slides by giving some examples and check the quality of our mesh.